Okay, looks like we're recording. Okay, so here's where we're picking up from last time. We finished section 1.2 last time, starting off with section 1.3, talking about the dot product. Good news. Y'all have all seen the dot product before. It figures in very big in linear algebra, and so I'm sure you recognize this formula. There's also a bunch of properties that are in the book. And again, keep in mind I have all these tough choices. I don't get to cover everything, and so this is a pretty clear didn't make the cut because again, A, it's a prerequisite, and B, it's a bunch of pretty straight up, as you would expect, properties in the book. Okay, so make sure to review all that stuff, make sure you're good. Just a real quick cultural point, just as a reminder, one of the things that's pretty cool about the dot product, it's the model that gives rise to this more general idea of an inner product. Extremely powerful, abstract, construction that allows for lots of different things. Image compression is one of my favorite applications of the idea of inner products, which comes from dot products, right? So that's just a, quick reminder. I do want to talk about the terminology a little bit. In at least one place, I found the book conflating these words perpendicular and orthogonal. A lot of people conflate these words. I think it's an unfortunate choice to conflate these. There are two different ideas that are both important, both deserving of a name, that need to be distinguished from each other, even though they're very, very similar ideas. And so here they are. Let's talk first about this geometric idea of there being a right angle between two directions. For example, two vectors, right? Well, if there's a right angle in between them, that's geometrically interesting. We need a word for that. I think perpendicular makes loads of sense. Notice, though, that this only makes sense at all if the vectors are non-zero. Doesn't make any sense to talk about what's the angle between this vector and the zero vector. The zero vector doesn't have a direction. It doesn't point at all. Therefore, it doesn't point in a direction. Therefore, it's not perpendicular to anything. That makes sense? Okay, now on the other hand, here's a closely related idea, but that's importantly different. And this is what I like to call an algebraic idea because I'm making a reference here to this equation of a dot product being zero. Purely an algebraic thing. Dot product is defined with a formula. That's algebra, right? Equals zero is algebra, I suppose. So now, closely related, sure, right? Whenever you have two perpendicular vectors, geometrically, they are orthogonal in the sense that their dot product is zero. Sure. But it doesn't go the other way. Right? Because if you have two vectors that are orthogonal, either or both of these vectors could be the zero vector, in which case they're not perpendicular. There is no such thing as perpendicular if one of the vectors is zero. Okay, so the way I see it, we have two importantly different ideas here. We should use different words for them, in my opinion. And it seems clear to me that because perpendicular is almost unavoidably a geometric statement, I feel like it kind of don't really have much choice in the matter. The orthogonal word should refer to the other one. So anyway, I try to be careful about this distinction. I was not brought up being upset about this distinction. This is something I developed later in my mathematical life. So I make mistakes sometimes, and I say orthogonal when I meant perpendicular and vice versa. And I will regret every single one of those. And please catch me on it if you do. Call me on it if you catch me on it. But try to be careful with that on your own. Okay. All righty. Okay. Unit vectors. This is pretty neat here. If you have a non-zero vector, but if what you need is a unit vector, in fact, the unique unit vector pointing in that same direction, there it is. Wonderful little formula. Nothing to it. You just take your original vector and you divide by its own magnitude. Easy to see that this result is a unit vector, and it's pretty handy to have a unit vector pointing in a given direction. So we're going to be doing a lot with this. Make sure that you're comfortable with not only that this is true, remember the formula, but also make sure to understand why. Right? So think through, persuade yourself that this is indeed a unit vector. Okay. All righty. Okay, new definition, something called a component. And a component goes like this. If you have some direction that you're interested in, whatever the direction is, very often we'll find ourselves describing a direction by way of some vector. So I'm going to suppose I have this vector v here, and so given that I have this vector defining this direction, if I have some other vector, w, and I ask, to what extent does w point in that direction? That's what we mean by a component. And the big idea here is that the component is, well, it's this far. That's how far w points in this green direction. Now, w also does a bunch of stuff sort of perpendicular to that direction, but I don't care about stuff that's perpendicular. The idea of a component is we're looking just at the part that's in the direction itself. Is that okay? Everybody happy with that? Okay. All right. Okay, so all of this said, how do we compute a component? Easy little trig argument. Here's the component. I can also talk about the magnitude of that w vector, and notice that these two things are part of a right triangle. And you got to love right triangles. Right triangles allow you to do trig. In particular, the cosine of that angle theta is that ratio, purple over blue. Everybody good? By the way, just a reminder, trig, I know it was a long time ago, but it's in the prerequisite trail of this course. Make sure you're good at trig. Trig's not going away. It's going to be all over the place in this class, so make sure you're good with your trig. Okay. All right, so you can solve, no big deal, for the component. There's a formula. I suppose you could stop here, but this is a fairly undesirable formula because, for one thing, if I am given vectors, what are the odds I know that angle? I might not know that angle. Furthermore, I would have to take the cosine of that angle, and cosines are weird. So kind of undesirable. A nice little slick move you can pull is to take this formula, and I'm going to multiply and divide by the same thing, namely the magnitude of v. Perfectly legal. Seems a little weird, but there's nothing wrong with it, right? You multiply and divide by the same thing, nothing happened. But conveniently, algebraically, now my numerator is exactly a dot product. Dot products are easy to compute instead of hard to compute. So real nice fact, this gives us a nice, where's my thing here? There we go. My alternative, much more desirable formula for component. Right there, no trig to be found. And it seems a little bit like a magic trick. Wait a minute, where did the trig go? What I will point out is that the trig didn't go anywhere. It's hidden inside of the formula for component and simultaneously hidden inside of the formula for dot product. It's still there. We just don't need to compute it, as it turns out. Okay, everybody happy? Real slick move. Okay, now I have an even better formula for the component. And it comes from making the convenient observation that, look at that, I have v divided by the magnitude of v. As previously noted, that's a unit vector. And I'm just going to reinterpret v divided by magnitude of v as u, this unit vector, and then check it out. My formula for component becomes this, I think, much simpler formula for component. You want to take a component of a vector w? Cool. Dot product it with the appropriate unit vector. Boom. rolls off the tongue really nicely. Components are dot products with unit vectors. Nice and easy. That make sense? By the way, this is on a list of reasons why it actually makes pretty good sense in a lot of cases to think of a unit vector as actually describing a direction. Right? If you think about it, in some sense, every vector describes every vector except 0 defines a direction, but other vectors also have magnitudes which are doing stuff and messing up formulas. Right? Unit vectors, if you think of a unit vector as describing just a direction, right, then it just fits really nicely that, well, here you're in some sense just dotting with the direction. U effectively doesn't have a magnitude to mess up that formula. So common choice to think of unit vectors as intrinsically describing directions. Okay. All right, moving along. Now, here's a very closely related idea. Not the same, but very closely related. I mean, after all, you look and you see this same right triangle. We again have a vector. We have a vector. And apparently we're looking to see to what extent in some way that vector points in the direction of another vector. And we seem to be interested in this thing here called a projection. And it looks a lot like the component. So what's the difference? And it's arguably subtle, but once you notice it, I mean, it's really an important difference. The projection is a vector. I do not mean by projection here the distance or any sort of a scalar quantity here. This is literally a vector. By contrast, notice up here, this component, not a vector. This component's a scalar. Right? And why do we have these two different concepts? Well, because sometimes you need a scalar, right? Sometimes that's what you're interested in. If you're playing football and the ball was here and then you get tackled here, how many yards did you gain? Scalar, not a vector, right? On the other hand, sometimes you might need a vector, and you could well imagine sometimes you might want to know maybe these are forces or something. Forces are intrinsically vectors. So sometimes you need one, sometimes you need the other. Real quick, I do want to come back to components, make another observation about what kind of a critter components are. And I say that there's a component as a scalar. Common misunderstanding is to think of a component as being a distance. It's not really quite right. Distances are intrinsically positive. There's no such thing as a negative distance, right? It's not a thing, right? From any location to any other location, what's the distance? It's always positive. The distance from A to B and the distance from B to A, always the same. They're not negatives of each other, right? So it's a mistake. It's sometimes a convenient crutch, and I'm going to commit this crime myself in about 30 seconds. But it's a mistake to think of components as being distances. They're not necessarily positive. Components can be negative. If we're playing football and if instead of this, right, if that didn't happen, if this is what happened, and I want to know to what extent did I make it downfield, well, I lost yardage, right? I have a negative component. Positive. Okay. All right. Okay, now let me commit that crime here. We are interested in finding the projection. Oh, yeah, question.
Wait, so what makes it negative? Is it like relative to the direction of V?
Yeah, that's right. If W is pointing that way and V is that way, and I asked to what extent does this vector W point that way? Well, negatively. Right? That would be a positive amount in that direction. This points somewhat in the negative of that direction. Does that make sense?
Yeah.
Yeah, cool. Yes.
I've heard these situations where the book says something like, what is the component vector of this?
What is the what now?
What is the component vector of some given vector? is that a component?
Yeah,
of that vector?
I'm sad to report that in different books they make different usages of these words, and I don't know that. Yeah, that it's just sometimes terminology, especially when things are pretty similar looking, like component and projection. Sometimes different books will make different choices. Sometimes even within the same book, they'll use the word in different ways. So no comment. I didn't write the book, so don't hold me to it. And I'm perfectly happy if different books make different usages. Whatever. So just this is a listener beware kind of a situation. Yeah. And so outside of the context of this class, if someone says projection, you should think, wait, what do they mean by that? Did they mean vector or did they mean scalar? Yeah. Great question. Okay, so how are we going to find this projection? Well, here's the thing. This projection is a vector. Vectors have magnitude and direction, and I'm going to make the observation that the direction it was messy. The projection is pretty easy to. The direction is pretty easy to write down. It's just the unit vector pointing in that direction. We have a simple formula for unit vector. So that the direction is just boom. There it is. It's u. Okay, so what's the magnitude? Now here's my little word crime. Apologies, I'll confess and make up for it in a minute. But the magnitude is the component. And so, okay, problem solved. The projection that I'm interested in, let's see, I'll do this with a blue. That projection is that product, which of course I can rewrite like that because we already have a handy dandy formula for components. Everybody on board? Okay, now the mea culpa. The magnitude isn't the component, right? Because magnitude is an intrinsically positive thing, component isn't. Right? So it is very handy, nice little crutch to kind of, you get the formula down and to, have a good intuition for it. But what I have to ask now is, does this behave the way it's supposed to? If this W vector, let's see here, let me erase, clean up. If this W vector weren't like that, if the W vector were over here, well, it remains that the unit vector is like this, right? That's what the unit vector is. And, well, the thing is, my projection would actually be like that. The projection would be, per this picture, it would be that blue vector. And notice that this formula that I wrote down naively is actually doing what it's supposed to do. This component here, being negative, would give me the negative multiple that I need of that unit vector u. So it works out. Is everybody with me? All right. All right. Now, the book has a different formula. Now, this is a matter of sort of personal preference. Suit yourself. The book makes the observation that this unit vector here, we have a formula for those unit vectors. It's v divided by its own magnitude. And you can write that down, and then you can further observe that that magnitude squared right there is a self-dot product. And so the alternative formula, again, feel free to think of projection by that formula. The book seems to prefer to think of projection by way of this formula. Now, pros and cons, and again, you have to ask yourself, what are we actually interested in here? What are we learning formulas for? If it is for the purpose of taking a given explicit vector v and a given explicit vector w, both of which you have numbers, and you want to turn the crank as fast as possible, well, this gets right at it, because this is in terms of v and w, and that's nice. But I think this formula up here is ultimately more natural. And I've kind of already made this case, but let me clean up my mess here a little bit. I've already made the observation that U is a direction. That's an intrinsically natural thing. This is a component. That is an intrinsically natural thing. So this formula is easy to remember because it relates one idea to a couple of other natural ideas. I like that, right? The way my head works, it makes it easier to remember. This formula down here, what's that thing? W.V over V.V? It's not really all that natural of a thing. Now I could make up some verbiage and I could describe it. It's not that it can't be done. It's just that it's not particularly natural. And then likewise, V. Why, if I am interested in a direction, am I using not a unit vector? It's kind of weird if you think about it, right? So to me, this formula has a lot of weird and arbitrary in it just so that it'll make the plugging and chugging a little easier. And I don't think that's a good trade. So I think this formula is, if you're gonna plug in, if you're gonna code it into a computer, yeah, maybe this would be better, right? But for intuition purposes and actually doing things, most of the time, I think this is the better formula. Does that make sense? Okay, real quick, tough choices and all that. I'm not going to have time to talk about this stuff. The book has several examples where they use vector algebra to prove certain facts of plane geometry. It's a pretty straight read. It's not that big of a deal. Give that a look. There is at least one exercise in the homework. I forget exactly. There may be two. I can't remember. But there's at least one exercise in the homework that will use these ideas of how the sums and differences of vectors allow you to prove certain cool facts about quadrilaterals and parallelograms, stuff like that. So take a look at those examples in the book. Be prepared to use those ideas in that homework exercise. Okay. All right. And we move on now to section 1.4, cross product. This is another topic I think y'all have seen at least some of in a linear algebra class. I know that they're a little bit more sort of brief about cross products than we need to be. So two things I want to say about cross products. First of all, there's lots of facts that we need to learn about how cross products and determinants and what I'm going to call geometric notions of order that relate to each other in weird and surprising and shockingly powerful ways. There's a bunch of these facts, and there's a bazillion different ways to kind of wind your way through and relate them to each other. Every book's different in how they do this. Every instructor has their own personal favorite way of writing down all these facts and relating them to each other. What the book has done is very good in a certain way. The things that make the book's presentation good are things that I don't think are really quite right for Math219. So the order that I'm going to be presenting these topics is different, and you're going to notice this. It's pretty dramatically different. So we're going to mention all the same facts. I don't think we have any actual disagreements, right? But the order that we present them and what we emphasize, you're going to notice some pretty substantial differences. Anyway, and it's no big deal, and this is very routine. The other thing I was going to say, there's, again, a lot to say about cross products and determinants and geometric notions of order, and it's too much. We just don't have time. So rather than leave out some of the facts, I, sadly for myself anyway, am going to leave out the proofs. And I don't want to leave y'all responsible for proofs that I'm not going to even talk about in class. And so y'all are actually absolved of, you have no responsibilities for the proofs that are in this section. Right? So that said, they are pretty cool proofs. correction, the proofs that are in my notes are pretty cool. I think now if you look at the proofs that are in the book's presentation here, I think you're going to find there's a ton of algebraic nightmare. Just like, wow, look at all it's really easy to get lost in the expanse of algebra that they find themselves in. So I think you'll like my proofs better than theirs. Anyway, again, you're not responsible for them. You don't have to look at them. I do want to make a last pitch. I encourage you to look at them because they're pretty cool proofs. There's a lot of good opportunities for mathematical weightlifting. Make yourself a better mathematician. Develop some geometric sort of understanding of these ideas. Even though you don't technically have to know the proofs, they will help you understand the ideas better. So, for your consideration. Okay. Here we go. So, geometric order of a list. I'm going to start with a two-dimensional version of this just because it makes a fantastic segue and it's much more immediately relatable. I'm going to talk about lists of vectors. A list is an intrinsically ordered thing. There is one of them that is unambiguously first in the list. And there is the next one, which is second in the list. Okay. So when we talk about an ordered list, I mean in that order. First one first, second one second. Okay. Now, I wrote ordered list here. Even though a list is intrinsically ordered, I wrote ordered here just as a double emphasis. Don't forget the order matters. Okay, so that said, how would I describe, for example, this pair of vectors? Now, see, look, I just committed a crime. I just said pair. It's not a pair, it's a list. The order matters. Okay, so this list where A is first and B is second. What geometric description should I give to the fact that this vector is first and that vector is second? And there's many ways to answer this question. I could say, well, we started with the shorter one and we ended up with the longer one. Right? I could say that they're in alphabetical order, but that's not geometric, and that's silly. Right? So what I want is something that's geometric in a way that relates to other things. And it turns out the best way to do this is to make the observation that this list, A first, B second, is counterclockwise. Anybody see that? Counterclockwise. Okay. Now, fine. What if the vectors were these over here? Now again, A is first and B is second. Now, what can I say about this list? Still, oh, whoopsie, wrong color. Still A first, B second. But now A and B being different vectors, notice now clockwise. Does that make sense to everybody? All right, so generically, I mean, most of the time, in other words, weird, annoying exceptions aside, it's going to be one or the other of these. It's going to be either clockwise or counterclockwise. So that's this is what I mean by the geometric order of the list. Okay. Now, we do have to talk about those annoying exceptions. Sometimes a list is neither like this list here, A first, B second. Well, it's not neither clockwise nor counterclockwise. And there's other versions of this. Instead of the vectors pointing the same direction, what if they were pointing exactly opposite direction? Again, neither clockwise nor counterclockwise. What if one of them was the zero vector? Again, there's nothing to say there about the order. So there are these various different cases where you would say neither. But here's the beautiful thing about it. They're all linearly dependent. That's a nice little sort of mental exercise to think through. Try to persuade yourself that anytime neither of these things happens, The resulting list of vectors always dependent. Something to think about. Yeah?
You said the order doesn't matter for that, right?
Well, it doesn't matter if the answer is neither. That's right. I mean, so in other words, if A comma B is dependent, then B comma A is also dependent. Yeah, that's right. Yeah. Okay. All right. So these annoying examples included, there are now 3 different versions here: clockwise, counterclockwise, and dependent. Okay. Now, who cares? Turns out, I think it's a pretty easy pitch. Clockwise, counterclockwise has some pretty natural properties. They are mirror images of each other. Right? If you have AB being counterclockwise, like those are, then check it out. They're reflections, A prime, B prime, clockwise. Right? And this isn't a sometimes thing. This is always. Clockwise always reflects to counterclockwise and vice versa. Okay. If you switch the order that you have them written down, if you put the first vector in the second position, second vector in the first position, and vice versa, right? Well, that'll always turn a counterclockwise list, right? A to B is counterclockwise there, into a B to A clockwise list. So this is another sort of always kind of a thing. Counterclockwise always trades to clockwise and vice versa. It's pretty cool. I mean, this is a natural property of this choice, using clockwise, counterclockwise to describe the order. And then lastly, independent of rotations. And I think this is a pretty easy observation to make. If you have an order that is counterclockwise, if you rotate those vectors, right, if you take this whole picture and you rotate the whole picture by whatever amount, rotate both of the vectors, the result still counterclockwise. So rotations don't matter. Does that make sense? My silly analogy for this is if you're looking at a clock and you see a second hand on the clock, if you turn your head to the side, it's still going clockwise. And if you turn your head the other way, it's still going clockwise. Rotations don't matter. Everybody happy? All right. Okay, now, again, that was a segue. I claim we're now going to do something analogous to that, but for 3 dimensions, and specifically for 3 vectors in 3 dimensions. We're going to come up with something kind of a 3-dimensional version of clockwise and counterclockwise. It's a little weird. Takes a minute to describe. Bear with me on this. Here's how it works. Again, I have an ordered list. So again, there is a vector that is first. There is a vector that is second. There is a vector that is third. Whoops, there we go. First, second, and third. I'm going to have to do some gesturing here. Won't come in the recording, sorry about that. This list we're going to describe as right-handed because of the following. This is arbitrary, by the way. There's some choices that got made long ago. So they're arbitrary, but they are standard, so we do have to stick with this. It goes as follows. Index finger of your right hand, pointing parallel to your palm, like if you're pointing at something. Okay. That index finger corresponds to the first vector in your list. Point it in the direction of that first vector, like I'm doing here. Okay. All right. Second vector, you're going to point with your middle finger. But you're only allowed to bend your middle finger the way middle fingers want to bend. No cheating like this. Right? So just bending toward your palm, you might say. So notice as I have my hand arranged here, I have my index finger in the direction of A. I have my middle finger bending the way it's supposed to in the direction of B. And before I go on, let me point out, between the two of these define a plane. Let me draw that on here. A and B define a plane like that. Notice my thumb points to a well-defined side of that plane. Now, in this case, the plane being kind of like this, right? I think it would be fair to say that my thumb is pointing on the upper side of the plane, or the top side of the plane, you might say, right? The language won't always work so conveniently, but in this case, I think it makes sense. My thumb here is pointing to the top side of the plane. Notice that this third vector is also pointing, as drawn here, to the top side of the plane, above the plane, right? So because the third vector is pointing in the same side of the plane as my thumb of my right hand, that's why we say that this is a right-handed list. Everybody buy it? Okay. Now, by contrast, here's one that is not a right-handed list. If the vectors were like this, as I have drawn there, and keep in mind, A is first, B is second, C is third. Okay, now let's try to make this work. Okay, I got to come over here apparently because I've got to point A, index finger parallel to my palm in the direction of A. And now it looks like I'm in trouble. I'm going to have to figure out how to get my middle finger to point that way, but I'm not allowed to cheat like this, right? Notice, though, that I can still do it. I don't have to point my index finger in the direction of A with my palm vertical. There's nothing magical about keeping your palm vertical. I can turn my palm however I want. My index finger is still pointing in the direction of A, right? So how am I going to get my middle finger to point in the direction of B? I'm going to have to turn my palm around like this. Now notice I've still got my index finger pointing in the direction of A. Now my middle finger is pointing in the direction of B and bending legally the way a middle finger wants to bend, right? Everybody happy? Now notice my thumb is pointing below the plane. C, the third vector, is pointing above the plane. Mismatch. So this list right here, ABC, for these three vectors, not a right-handed order because my thumb's pointing down, the third vector C is pointing up. Lose. Everybody happy? But it is left-handed. Nothing to it. Everybody happy? So not hard to persuade yourself most of the time. I mean, unless something weird happens, right? Like this case over here. Unless something weird happens, your list is either going to be right-handed or left-handed most of the time. Generically, we say. Okay. All right. So again, there's all these annoying little sort of other possibilities. And again, there's a bazillion different versions of this being parallel to that, or maybe they're all parallel to each other, or something zero, or two of them are zero, or all of them are zero. It's whatever, a lot of different cases. They're all linearly dependent. Okay, yeah?
We're assuming that the direction towards the page is the, well, so-called smaller angle.
Say it one more time, I'm sorry.
We're assuming that the direction coming out of the page is the so-called smaller angle. Right?
Smaller angle.
So coming radially this way.
You're talking about the way I drew it?
Yes.
My intention was that A was kind of like this, out of the page. Yeah, all three of these vectors are coming out of the page. Yeah, and it's really hard to draw, and indicate that. Yeah, but that's right. Yeah. Yep.
What if they're not perpendicular or dependent, somewhere in between? Like,
What if one more time? I'm sorry.
what if they're not like perpendicular or dependent?
Yeah, no. Importantly, they don't have to be perpendicular, right? So all I need is the first two vectors define a plane. That third vector can point anywhere on the thumb side of the plane. It doesn't have to be perpendicular. It could be like this, As long as it's on the correct side of the plane, that's all that matters. Is that okay? Yeah, cool. Anybody else? That's good. Okay. All right. Okay, so I claim that this is actually pretty analogous to clockwise, counterclockwise. And remember, the conspicuous properties of clockwise, counterclockwise is that they're mirror images of each other. If you trade two of the vectors, that changes the order, and it's independent of rotations. And check it out. Right hand and left hand are mirror images of each other. If you trade any two vectors, that changes the order. Now I'm going to have to kind of draw some pictures here, but if you trade A and B, right, then ABC is right-hand order, but BAC is left-hand order, right? So whenever you trade two, just like I've done here, whenever you trade two of the vectors, that's going to turn a right-hand order into a left-hand order. And order is independent of rotations, and this is a pretty easy pitch right here, because after all, if you have a trio of vectors, and if this is right-hand order, well, my right hand, if I rotate everything the same way, is still my right hand. So however you rotate these vectors, looks like I rotated them like this. Here, okay, fine, whatever, still my right hand. Everybody buy it? Yes?
Can I ask something on the second one? So
Yep.
You said that trading positions of two vectors and let's change the order.
Mhm.
It doesn't matter which two vectors it is, right?
Correct. This was not a proof. This is a for example, not a proof. That's right. But you can switch any of the two, just trading the positions of any of the two, and yeah, that's right. Yeah. Yes.
So then if like three of them switch, would it be like you do two swaps?
Yes, that's true. Yeah, and that's actually going to get me to the next thing but you're right. Yeah, that's right. Trading sort of. Let me just get to the next thing. Yeah, right. Okay. Now there isn't really a good two-dimensional version of this one, but I call this cycling. And so in particular, if you the third vector, put that into the second position. The second one you put into the first position. The first one falls off, and then you just put it around over here where the third one was that you just vacated. So everything kind of moves over by one, and then the one that falls off goes back to the other side. When you do that, that preserves the order. And to your question, when you do this, when you cycle, that is effectively two trades. And so that changes the order twice, in other words, and thus preserves the order. So again, yeah, it doesn't really make much sense in 2 dimensions, but it's a nice sort of new fact for 3 dimensions. Yeah. Okay. All right. So right hand, left hand has all the same 3 features that clockwise, counterclockwise. It's pretty naturally thought of as a 3-dimensional version of clockwise, counterclockwise. Okay. All right. Now some theorems about determinant. I'm going to have to be kind of quick with this. Again, we're not going to prove this fact. Actually, I don't even have this proof in the notes. It's a little heavier than I think is 219 appropriate. But neat fact and very important, powerful fact. If you have a list of vectors in R2, 2 vectors in R2, you can make a matrix out of that list. All you have to do is take the first vector, make it the first column, and the second vector and make it the second column. Boom, list makes matrix. Yeah. If you have a matrix, you can make a linear transformation. If you have a linear transformation, you can talk about what does that linear transformation do to the first standard basis vector? And well, of course, it gives you the first column, namely the first vector, A. And along those same lines, you can ask, what does it do to the second standard basis vector? We love standard basis vectors. It gives you the second column, namely B. which means that, and again, let me walk through it again. If you have a list, you can make a matrix, and by which you can make a linear transformation, and then by looking at what that does to the unit square, that then makes a parallelogram. Now, I want to point out, I haven't really made any statements yet. I've built some things, right? You give me a list, I make a matrix, I make a transformation, I make a parallelogram. There's a lot of arbitrariness in what I've written down here. Why do we use columns instead of rows? Why did I look at the standard basis vectors, right? The arbitrary choices. But with all of this built, now I can make an actual statement of substance. And this is a jaw dropper, I think. The determinant equals the area, absolute value of the determinant. But really surprising fact, because we're talking about this matrix, we're talking about this parallelogram that we associated to it. They're completely different kind of critters, but the absolute value of the determinant of this thing, the area of that thing, are always the same. Really surprising result. Really not obvious, but true. Everybody with me? I'm also going to point out pretty counterintuitive. Think about high school geometry. How would you have computed this area? You'd drop a perpendicular right here. You'd compute the length of that height, the length of this base, right? But the length of that height has trig in it. The length of this base has square roots in it. Where's the trig and the square roots? Right? I think it's shocking that this trig and the square roots just don't, it's like they cancel out or something. It's phenomenal. Determinant, 3-function arithmetic. Add, subtract, and multiply. Answers a question that would otherwise involve trig and square roots and ugliness. Amazing fact. Okay, let's see. Another fact here, and I'm going to have to zoom out to talk about this. Let's see here. The sign of the determinant indicates the order. So keep in mind what I mean by sign. We're talking about determinant of this matrix, right? Determinant could be plus or minus. Sign just means which one is it? Is it plus or is it minus? Order refers to the order of the green and blue vectors here, and keep in mind there's A and there's B, right? So B is second, A is first. And shocking fact, if the determinant of this matrix is positive, let's see, let me get back down to here. If it's positive, then this order will be counterclockwise. Another shocking fact, I mean, where'd that come from? How could that be? It's very surprising. Furthermore, it goes the other way. And I'm going to have to fiddle with my picture here. It could be that A would be there and B would be there, in which case that's the image of E1, that's the image of E2. And in this case, what we would find is that this determinant would be negative, corresponding to the fact that this list is now clockwise. So negative determinant means clockwise, positive determinant means counterclockwise. Surprising, but true. Yes?
So if the original list was clockwise, what do we mean by the plane is inverted?
Yeah. I'm getting to that. I'm getting to that. Yeah. So let's look at what we have here now. In this, and I'm going to leave it right here with A over here, B over there. So this is clockwise. The determinant's negative. Let's think about what this linear transformation does. this linear transformation takes vectors to other vectors. Okay, sure, but look at this list. E1, E2 is unavoidably counterclockwise. So this linear transformation has taken a counterclockwise list and turned it into a clockwise list. What would a linear transformation have to do to turn a clockwise into a counterclockwise? I claim stretching won't make clockwise turn into counterclockwise, right? Stretching doesn't change orders. Rotating doesn't change orders. Shearing wouldn't change orders. Only reflections. This is what I'm calling an inversion, right? So it's like you're reflecting through a line somewhere in the plane. And so that's just another way of saying the same thing. If determinant's negative, you can view it as a statement about these vectors, but you can, I think more importantly, view it as a statement about this transformation. Negative determinant means that the corresponding linear transformation has a reflection in it somewhere. And we're out of time, so we'll have to draw the line right here. We'll pick up here next time. Y'all have a great extended weekend. See you on Wednesday.